So you work with Postgres. You put data into Postgres, you do inserts, updates, and deletes, you select data back out, you're comfortable writing queries, maybe even designing a table or two. But what happens when a query goes slow? When you've got a select query that's not running as quickly as you'd like, why is it running slowly? And what can we do in order to make it go faster? Let's talk about the very fundamentals of a select statement inside of Postgres. I'm going to demonstrate it using the Stack Overflow users table. The Stack Overflow users table holds exactly what you think it holds. I'm going to go grab just 100 random rows out of there and zoom in. The Stack Overflow users table, it's got an ID on it, starts at 1 and goes up to a bajillion. And this is everyone who's ever created an account at stackoverflow.com to go post a question, post an answer, whatever. It's got their names, it's got the last date that they access Stack Overflow, it's got things like their location, their website URL, and their profile. I want to go find the people who live near me. Tunisia, that sounds interesting. I live in Las Vegas, Nevada. So let's go find the people who live near me. I'm going to run a query that says select star from users where location equals Las Vegas, Nevada. And the first time that I run it, notice that I didn't have an order by inside there. The first time that I run it, I see U.S. support, David Figueroa, Jim Kelthau. Let's go execute that again and go see what happens. Video Poker, that's kind of funny for a name. Colin, Gorilla, execute it again. QPID, Eric. In Postgres, order is not guaranteed unless you put an order by in there. You may have worked with other databases. You may have seen that are rumored that, oh, your order by isn't guaranteed. In Postgres, it is really true. Order is really not guaranteed unless you put in an order by. Well, obviously, I want to see the same users every time, and I probably want to see the people who have, say, the highest reputation scores. So let's modify our query and let's say, go get me the top 100 users whose reputation score is the highest. And you notice it's taken a few seconds there. So here we have it. Number 1, Eric Funkenbush. Congratulations, Eric. Number 1, James Moeller, and so forth. Now, that took a few seconds in order to run. Let's hit execute on it again. It takes a couple seconds in order to run there. When you have a query that's taking some time, it's really tempting to say, well, it's cached, right? Not exactly. The source data is cached, but only the source data, not your final results. Let's think about what work that Postgres has to do in order to go find the people whose location equals Las Vegas and or sort them by reputation descending. To figure out what work Postgres is doing, Postgres has a built-in command called explain. I can rerun the same exact query and run it with explain at the beginning of the query. And that tells Postgres, I want you to go give me a a written explanation of what it is that you did. And when you read these, you can read it from the bottom up. I don't know about you, but I don't really work very well with big walls of text. Because, of course, your explain plan isn't going to look this simple. Your explain plan is going to be 5 miles long, and trying to find anything out of it is going to be like trying to find a needle in a haystack. So I need a visual way to understand what's going on inside this. That's where plan visualization tools come in. And there are lots of totally free ones. The one that I like using is explain.dalibo.com. We're going to paste our query plan into there, but I want to notice that down at the bottom it says, for best results, use explain with these options, including format stuff to JSON. So let's take those exact same explain options, and instead of just running explain, let's go run explain with all of those options. I'm going to highlight it and hit execute and zoom in. One thing that I do want to point out here is that when you run queries with explain, you're still running the query. So keep that in mind. If the query takes 10 minutes to run, or if you're doing all kinds of inserts, updates, and deletes, just be aware of that. So here for selects, because this class is about selects, we've done the explain. It's dumped the stuff out here into JSON. I'm going to copy it. I'm going to go over to Dalibo and paste it, and then click submit. Now, whenever you click submit on, especially when you're inside a web browser, like here I'm on explain.dalibo.com, when I click submit, I am actually sending my plans, depending on which visualization tool you use, you can be sending your plans out to the internet. If your plan has anything confidential in it, client names, patient names, financial stuff. It's even your table schema may be proprietary and private to your company. You may not want to use these tools. There's a solution for that. If you go down to the bottom of most of these tools, they all have, well, I say they all, most of them have a little help or about sections where they give you links to go download this locally so that you can use it locally without sending your stuff to the internet. Here, of course, I'm dealing with Stack Overflow public data. I don't really care if people see it, so we'll just go ahead and click submit. When I click submit, I get a really nice visualization here that shows me the different operations that my plan did. And generally speaking, I'm going to look for the icons. These icons indicate problems. Boy, do I have problems. So the clock icon indicates the part of our query that took the most time. The $ icon indicates the part that Postgres thought was going to be the most expensive in terms of executing the query. And then the filter indicates places in the plan where Postgres read a large amount of data and then filtered it out to only find the rows that you're looking for. Generally speaking, you want to find the icon or find the operator in your plan that had the most icons on it. And let's go expand that and let's go see what it was doing. Let's move it around a little so we can zoom in a little closer here and see. So what did this thing do? It scanned the table. Now, you're like, Brent, how did you know that? Well, it says parallel sequential scan. Parallel meaning it had multiple CPU cores involved because Postgres knew it was going to be a lot of work. Sequential because we're going to scan the whole table start to finish looking for the people who live in Las Vegas. Your immediate next question is like, wait a minute, Brent, can't Postgres just jump directly to the part of the table that has the people who live in Las Vegas in it? No, more on that in a minute. Doesn't know where they are, literally, that they're in Las Vegas. So it's going to scan through the whole entire table, and it read 22 million rows. Because we got 22 million rows in our users table, it removed 99% of them because our filter is only looking for the people who live in Las Vegas. Generally speaking, and you'll hear me say that a lot because this is literally the very first class that you're going to take from me, and you'll have all kinds of exceptions along the way. But generally speaking, we want to read as little data as possible right from the get-go. We don't want to read all 22 million rows and filter out 99% of them. We want to jump directly to the people who live in Las Vegas. And then the clock icon here is because this was the longest part of our query. This took 743 milliseconds. Now, granted, 743 milliseconds may not seem like a lot to you. This is just showing whichever part took the longest because Dalibo guesses that you're here because you want to troubleshoot the query because it's not going quickly enough. In terms of costing, Postgres tries to guess how expensive different parts of the query are going to be. This is just a generalized unit of measure here. It doesn't correspond to time. So if I want to make this go faster, I want to read less rows. I don't want to scan the whole entire table looking for the people who live in Las Vegas. I need a copy of the table that's sorted in a way that will make my operation go faster. And to do that, I'm going to go create an index. So the index that I'm going to go create, I should start the index creation here while I zoom in and talk about it. The index that I'm going to go create says, hey, Postgres, I want you to look at the users table and create a copy of this table that's sorted by location and then reputation. When you see create index, it literally means make a copy of the table. Now, the more copies that I make, the larger my database is going to become, the slower my inserts, updates, and deletes are going to be, the longer my backups are going to take, the longer my restores are going to take, the longer vacuum's going to take. Pretty much any maintenance task you can imagine is going to take longer. But the payoff is that if you have a copy of the data sorted by the way that you need it, like here I just want to dive bomb into the people who live in Las Vegas, and then I want them sorted by reputation so I don't have to sort them every time. If I have a copy of the table set up like that, then my query is going to go much faster. Now you'll notice that this did take some time. This is a relatively small table. It's the smallest one in the Stack Overflow database, and yet it still took about 30 seconds in order to go create that index, because Postgres has to read the entire source table, write out all the locations and reputations, sorting them all, and then write that final copy back down to disk so that our indexes or that our queries can use it. Well, now that we've got that in place, let's try to run our query again. And first I'm just going to run the query without explain on. 3, 2, 1, execute, done. 3, 2, 1, execute, done. It's executing immediately. People wouldn't bring you a query this fast and ask you to analyze it, but let's run the explain plan so that we can see what's going on. I'm going to copy it out, and I'm going to start a new window for our explain plan so that we can compare back and forth between the two. I'm going to paste my new plan in and click submit. This plan doesn't exist. Listen, paste, submit. There it goes. Open source. When it breaks, you get to keep both pieces. So here's our new query plan. If I zoom in on this, now our new query plan had the most expensive part, the part that took the most time and the part that was the most expensive now shows up as this index scan. So we can see the Postgres used our index on location and reputation. But it's way faster now. This work is now down to just 100 or less than 1 millisecond, 0.114 milliseconds. So it ran in less than a millisecond. You'll notice that there's no filter icon on here because Postgres didn't have to read through a whole bunch of rows trying to find the people who live in Las Vegas. This index is already sorted on location. The other thing that's missing from this plan is that there's no sort. To see that, let's go look at the old execution plan. The old plan had a few different operators in here. It scanned the table, then it sorted the rows that are involved. There's also a gather operation because this thing went parallel across multiple CPU cores. But now, because we have so little work, this operation also didn't go parallel across multiple cores. We got rid of the sort and we got rid of the gather. Magic, the query just runs faster. But why? What's the magic underneath indexes that helps Postgres get to this data really quickly? To understand why, we really need to understand how Postgres stores this data to begin with. And what I've done is I've visualized it for you here. I visualized it for you in the form of a piece of paper. And in the show notes, I actually have this piece of paper, well, not the piece of paper, but a PDF that you can go download. Postgres, by default, stores your data in 8K pages. You could compile it with a different size, but generally no one does, and even if you did, it's just a different sized piece of paper. Postgres stores your data in pieces of, well, not paper, but 8K chunks of data. And that chunk of data is the same whether it's on disk or up in memory. You can think of this as like the smallest unit of data that Postgres works with. This data, how is it organized? We'll look over on the far left-hand side and you'll see a CTID. The data appears to be sorted by this CTID. What is that? CTID is an internal column that Postgres puts on, just like Xmin and Xmax, and you didn't ask for any of these three when you built the table. It's just something that Postgres put in behind the scenes. That first column, CTID, it's two numbers. The first number is which page we're talking about. And then the second number is which row it is on the page. Now, I'm generalizing a little in here. Sometimes we're going to have experts who are like, it's not technically a row, it's a tuple. Yeah, okay, we'll talk about that in other classes. But for now, just think about your table being a big stack of 8K pieces of paper. There's page 0, page 1, page 2, page 3. And if I want to find the people who live in Las Vegas, they ain't sorted in that order. They're not sorted by that order, but they could be. And that's where indexes come in. When we created our index, we created another set of 8K pages. And those 8K pages look like the black piece of paper in your handouts. First thing that you're going to notice is that this is two separate pieces of paper. Your ordinary table itself is stored on one set of 8K pages. Your index is stored on another set of 8K pages. And when I created an index based on location and then reputation, when you create an index, you get to pick which columns are on these 8K pages. Notice there's less. All I have is location, reputation, and CTID, and that's it. I don't have display name or about me or those other columns. So I can fit more people, more users per page here. That's why we have a column here for Las Vegas. We have another column over there and another column on the far left. In this example, we can fit roughly 3 times more users per page than we do on this. Your indexes are generally speaking going to be smaller than your base tables. Notice that it also stuck CTID on here. Well, why indexes are so useful is when I say I want to find all the people who live in Las Vegas, Postgres can dive bomb into just the Las Vegas area. And then for every row that it finds, it can go use this CTID to go look up where the rest of the columns are. Because my query, when I said show me the top 100 users in Las Vegas, I didn't say just show me their location and reputation. I said select star, because I also want to see their name and their about me and their creation date and other stuff like that. This CTID column, oops, I'm pointing at the wrong specific part. There we go. This CTID column facilitates joining between these two objects. Postgres had to read both of them. Postgres seeked into the Las Vegas area, made the list of the CTIDs it had to go look up, and then looked up over here to find the rest of their data. You can see that in the plan. If I pop back over to my plan visualizer and I look at the query plan here, it says it found relevant records based on an index. Index scans actually do 2 read operations, one to read from the index and then another to read the other values from the base table. Both of those reads are just collapsed down into this one operator. Depending on your plan, sometimes they're not the plan visualizer, but the query in the plan itself. Sometimes they're collapsed down into one operation. Sometimes they'll show up as 2. Some plans will show one operation for the index and another one for the underlying base table. Okay, so there's also not a sort, because if I go back in here and I look at this index, so if I asked them ordered by reputation descending, what's Postgres going to do? Postgres is going to seek to the part that has Las Vegas, and then it's going to go to the very last one. It's going to read backwards. It's going to read from this end down to the tiny end. So you can kind of think of it as a couple of index seeks. It seeks once into Las Vegas, then it seeks to the highest number and reads backwards. You can see that on the plan too. Over on the plan's details, there's this miscellaneous tab here. If I click on the miscellaneous tab, it gives me all kinds of other stuff like scan direction equals backwards. Now again, this doesn't mean that I scanned the entire index. It just means that I jumped to Las Vegas, jumped to the highest one, and then scanned backwards. When I created this index, I didn't have to tell Postgres I want this data to be sorted descending. For most cases, for most use cases, you don't need to specify descending on your indexes. Places where you do is when you start flipping back and forth in the order in the same query, like sort by this descending, then this ascending, then something else descending. That's when it starts to matter. Okay, so in this case, this clearly makes our query go way faster, but the more indexes that you pile on, the slower your inserts, updates, and deletes will be, the bigger your databases will become. And by right about now, you're like, wait a minute, okay, so let me go see what indexes my own tables have, and we wrote a utility to help make that easier for you. This utility is called check indexes, and it's part of our bag of tricks over at Smart Postgres. So here what I've done is I've said select star from check indexes, and then I passed in the schema and the table that I want to look at. If you wanted to look at everything, you can pass in nulls for both, but the data is going to be kind of overwhelming. Just stick with looking at the one table that you're having problems with. Now again, when you're trying to figure out which query or which table is having problems in your big ginormous plan, what you do is go paste your plan into a visualizer like Delebo's, look for the icon or look for the operator that is taking you the longest, is the most expensive, and especially is filtering out rows. Filtering out rows means that Postgres doesn't have a copy of your data organized in a way that makes this retrieval easier. Then look at what table this is. In this case, I'm looking at the users table. You may have an index on here, it just may not be the right index. So here for the users table, for my public users table, if I pop over and look at what my indexes look like on public users, you're going to run select star from check indexes public users. Then what this does is it gives me, there's a schema and a table on here, but I'm going to zoom in just a little past that so that, and set this up a little so I can zoom in and show it to you. So here it gives you the list of indexes that are on the table. It includes the table itself. So here we have the ordinary table, which is in our handouts, the white piece of paper, the table itself. It shows you how large that object is, in this case 2.8 gigabytes. The number of rows that we think are in the table. This may be inaccurate depending on vacuum and analyze, more on that in our other classes. So here, if I don't have indexes to help support my query, if I don't have something that'll help me jump to the rows that I'm looking for, then Postgres is going to have to scan the table, and the larger that your data becomes, the more problematic this is. This is one of the many reasons why applications work so well in development environments and then start to catastrophically fail in production as we add more and more users. It's also one of the reasons why it's hard to compare query performance between production environments and development environments, because you might have a dev environment that has hardly any data in it, and when you run your queries in it, they're blazing fast. However, out in production, they fall apart because Postgres is having to do all this filtering of data that we don't care about in order to get the juicy data that we do care about. Check index also gives you the index definitions on here with the exact create index statements that you could use to go. What this helps you do is see what the columns the index is on, because after all, sometimes we name our indexes in a little goofy ways. The names don't always reflect what's actually in them. So if you widen out that check indexes column, you can see the columns that the index is on. Now, you may have redundant indexes. You may have multiple indexes that are on the same columns. You may have overlapping indexes. Generally speaking, this is where when I'm going to give you one of those general consultancy type answers that drives people crazy, you want to have enough indexes that your selects go fast, but not so many indexes that they slow down your inserts, updates, and deletes, your backups and restores, your vacuum and analyze jobs, and just make the database larger overall, because often in the cloud we have to pay for that stuff. This becomes part of a kind of a lifelong journey here of walking this balance to have enough copies of our table that our queries go fast, but not so many that our queries go slow. You can start investigating your own tables with our check indexes. And if you go to smartpostgres.com, we show you how to get it over at the top as part of our box of tricks. Well, there are the fundamentals of select statements. Hope you learned something. If you enjoyed, like and subscribe, and we'll see you in the next episode. Adios.